many people simply say, oh, that's a stress peak and ignore it. But sadly, that's obviously not the right approach. You should use like nonlinear FEA to see how this works. And there are failure mechanisms that you can encounter, like plastic collapse or shell buckling, and to realistically analyze those, especially since shells in civil engineering tend to be very slender. You actually absolutely need nonlinear FEA. There is no, like, there are equations in the code, but there are so rudimentally and so governing safety factors that if you want to have an economical design, nonlinear FEA is basically a must-have. You have to think through what you're doing, and the engineering judgment happens at the level of how many load cases you wish to analyze. And we can quite greatly reduce the amount of load cases. But when you have that, there are no compromises when it comes to mesh quality. So I could build a model that would run nonlinear analysis in like 20 minutes, maybe. But the mesh would be so bad that the outcomes from the analysis would be basically useless. So we build models that are very nicely meshed, and they run for like 3, maybe 5 hours each. So effectively, what you do is you have several computers with several licenses, and we have very strong machines, and you run several analyses in parallel, and you simply run them overnight.
The complexity of FEA and the solution architecture and all this kind of stuff. But ultimately, it is a tool, and the skill of the engineer
absolutely
to look through the problem and use that tool in an efficient, effective manner that works for you. If you're going to run those 100 load cases and you press go, and you've got some massive cloud solver capability, but you're still taking a week to find the results, it's not going to work for anybody, is it?
I feel that if we develop those tools too fast, they will simply become magic, and people then will sit in front of the computer, perform some sort of engineering rite or a ritual, press play, and get the outcomes. They will worship the outcomes, print the report, send it out. And there will be less and less engineering involved because the complexity of it is too high.
In this episode of The Simulation Stack, we feature Łukasz Skotny, a leading expert in simulation and nonlinear FEA. Starting with a passion for simulation, Łukasz developed one of the first online FEA courses, and through his company, EnterFEA, worked with the civil engineering and related industries to optimize designs and avoid structural failure. In our conversation, we'll explore how he mastered FEA, navigated commercial software, and applied nonlinear FEA to solve real-world engineering challenges. He'll also discuss modern obstacles to learning FEA and why engineering judgment remains crucial, even with advanced simulation tools.
Right, Łukasz, thank you for joining us.
It's a pleasure to be here, mate.
You are a superstar in the FEA community.
I never started to think this way about myself. It's but I recently was teaching a session on NAFEM's conference, and actually few people recognized me, so it's like
that's good.
Maybe there's something to it.
Cool. Okay, so when I start these conversations with people, I like to find out where people are in the world, first of all. So you're in Poland?
Yes.
Whereabouts?
I'm in Poland, in a beautiful city of Wrocław. If you ever come to Poland, Wrocław is the place to go. It's just wonderful.
Yeah. You mentioned you have lakes there and nice countryside, and
yeah, it's like, first of all, it's a very beautiful city with some pretty cool monuments, but like the quality of life here is very, very good. And nearby there are lakes, and yeah, you can, like, there are districts that are just awesome. So if you consider living in Poland, which I advise, Wrocław is like a really good.
Awesome. And quite a historical city where you are there.
Oh yeah, absolutely. But in Poland, this is rather a given. Gotcha. Most cities are like historical in nature.
Yeah. Good stuff. Cool. Okay. Well, I just wondered, maybe rather than me introducing yourself and your background, if you could perhaps put into your own words how your career, well, who you are, first of all, your full title and experience, and how your career has progressed
Okay.
so far.
So my name is Łukasz. I decided to study civil engineering mostly because of the influence of my father, who also has a PhD in civil engineering.
Okay.
And then just after finishing the studies, I started my company. And at the same time, I started my PhD. So if you ever want to attempt that, that may not be the best idea. Luckily, I'm a workaholic. I'm a bit better now, but I actually was able to work like 16-hour, 7-day weeks. It was pretty insane. And I did a PhD in shell stability. And few years afterwards, I realized that I don't want to do like a classical civil engineering anymore that I did. So I started a second company, EnterFEA, that basically does FEA. And back then, I wasn't really thinking about doing training at all. I just did what we do till today. So we do FEA design. That's the core of our business. But since I was still working at university because I was a lecturer for a decade, I traveled to many international conferences and I've met few people and I befriended some of them. And one of those people was Ola, and she's a CEO of a software company here in Poland. And she called me once a few years after we first met and said, hey, somebody called us and they want training and like maybe you could come with me and we'll do this together. I know it's like your strength. So I said like, okay, let's do that. So that was how I started. And firstly, it was like in-person training, corporate stuff that I went to and do like 1-2 day gigs, teaching people things. But at the same time, maybe a bit earlier even, I started my blog, mostly to like do it. It was not a project, like I didn't consider it like a business part, more like for fun thing. And then the blog grew and it started taking more and more of my time. And it was like with every hobby, more and more difficult to justify the effort involved. And at one point, somewhere around the time of the first training, the live one, I came to realize that if I want to continue blogging, I actually have to earn somehow on it because the amount of time that goes into it is so insane that I simply need to have some sort of justification. So I decided to make a first online course. I planned to deliver it in 6 months. It took me 2 years to do it. And then after the success of the first one, I decided to make the second one. And that time I thought, yeah, now I'm so much smarter. I know how this works. So it will take me 6 months. And again, it took me 2 years.
Oh, wow.
So yeah, I guess that 2 years is just the amount of time I need to develop a course.
2 years to develop a course. Wow.
Yeah. And here we are, and I'm working on a third one, thinking that, yeah, it should take like 6 months.
Yeah.
We'll see where this goes. But that's more or less how it went. And I somewhere along the way, after 10 years, I quit university. I really liked teaching, but it was too much effort, too much paperwork, and many things I didn't enjoy at all. So I guess that training, both corporate and online things, kind of like feel the need of me to teach others, which I still enjoy. But business-wise, it's okay to do those courses, but like the core of the business is to do design, and I can't treat training more or less like anything else than a hobby. It's still.
Sorry, that's interesting. I've spoken with a couple of people recently who've had long careers in academia and then moved into the software development side of simulation and what have you. And what type of stuff are you teaching in the university then?
I was teaching structural steel design And since I had a PhD in shell stability, I mostly taught shell structures. Our university was like one of the very few in the country who had subjects that were not PhD grade related to shell stability. So I was mostly teaching those, but also like, you know, industrial design, those classical structural steel civil engineering courses. Like industrial buildings, the towers, masts, things like that. And then, but my expertise, so the most courses I did were on shell structures, like silos, tanks, and so on.
And the people who would graduate from those types of courses, what kinds of jobs or roles or, you know, aspects of the industry would they be looking at then? Would this be building design or bridge design or like the silos that you mentioned?
Funny enough, in Poland, there is actually a division between bridge design, which is like a separate specialty on the university, and in some sense, everything else design, but the everything else is further divided into things. So the students that would like to pursue what I taught in my courses would, I guess, do something I would refer to as industrial design. So there is like an industry and they needed like factories. So you need buildings there, equipment there, silos, tanks, some sort of machinery, although not machinery in a sense that, oh, I need to design an engine or a device, but rather like housing for it or supporting structure for it and so on. So so that would like catwalks and all, but catwalks are, you know, it's not a very glamorous thing, but that would be the kind of job you would be searching. But of course, like those courses were only a portion of what you've learned at civil engineering. So people did a lot of various things afterwards.
I mean, my background is in the aerospace industry, so there's a very different requirement on the structural element, if you like, that you're involved with. Of course, you know, our structures need to be super light and, you know, transport hundreds of people. Yours need to be able to withstand earthquakes or whatever. You know, it's a very different. I've probably done a disservice to the loading environment there completely, but it's a very different design development process, end product. But there's a considerable overlap, isn't there, in terms of the mathematics, the skills, that, you know, the simulation tools that we use. I mean, I know that you tell me, but you do a lot of your work with Nastran, I believe. And historically, Nastran has come from, you know, the early days of NASA's development into computational structural design. You know, so it's you know, massively different, yet overlaps in there as well. You know, so interesting to hear the types of things that people were going on to do and to look at. You know, go on. Sorry.
I think that the biggest hurdle in civil engineering is that we don't do tests of the designs. There is no way to do that. If you're designing a huge factory, like it's not like a car component that, you know, 10 people designed and you manufacture several various test pieces. You test them extensively and then they go into mass production. Everything you do in civil engineering, well, not everything, but most of the things you do are just one-off projects, which means that there will be no prototypes. There will be no testing. You just have to be certain what you're doing from the start. And the responsibility associated with that is very high. So I guess that would be the biggest hurdle. And I know, I'm not sure how it looks in aerospace, but I know there are many in many industries where this is not the case because you can test things out and this makes it a bit easier on the responsibility side, let's say.
I mean, from an aerospace perspective, obviously a full wing test. I don't know if you've ever seen something.
I've seen it,
you know, but you know, a full wing development can take 5 years, you know, just to have that wing ready, you know. So there'll be teams of simulation people or analysts beavering away on these design developments, and then they have a pretty good idea of what the structure is going to be doing, you know, before you can go anywhere near the physical test, you know.
And in civil engineering, it looks like that you have a guy who has like who's chartered, like I am. They have like a national exam that allows you to design stuff, and then there are like 2-3 assistants, and they can design a skyscraper. by design, I mean not necessarily draw, but rather do all the calculations that will ever happen, and this can take like a month, and that's it. Like there's not so the pressure, the time pressure, cost pressure, and so on is very high, because when you think, oh, we'll mass produce this airplane, and there, like the wing that you design will be used so many times that it makes sense to develop it. Here, everything is a one-off. So
that's true.
It's tricky.
I mean, I don't know whether this is something you can answer or whether it's easy to wrap around. But from an aerospace perspective, you're developing to between a 1.25 and a 1.5 safety factor. Okay, so anything less than 1.25 is well, it does depend on the condition. In some cases, you can go up to 2, but anything less than 1.25, it's dangerous. Okay, anything above 1.5 or 2 is too heavy. So you're trying to capture this band, if you like. So, you know, do you have a handle on the kinds of safety factors that?
Well, we'll very quickly get into probability, because when you say in aerospace that you have a safety factor of 1.5, my question instantly would be, how did you derive the value of the load? Because you have to have some sort of load described, right? And then most likely some team of people did a lot of statistics to calculate that usually we experience load in this distribution, and we're treating like 5% value, so the 5% probability of exceeding to be the value you will use at the design, right? And then when you calculate strength, the material is usually stronger than what the code tells you to take into calculations. And again, this is probabilistic thing, right? So in the end, I'm not sure, like in civil engineering, we often use 5% values. So there is 5% chance that the material will be weaker than what you assumed. There is a 5% chance that the load is actually higher than what you assume, and so on. But of course, this means that there is a 95% chance that things will be stronger and the load will be smaller. Right? So assuming that in aerospace, you have the same 5% rule, although, of course, this is way more complicated than vanilla 5%. I would say that the safety level seems more or less on the same level. Most of the loads would be multiplied in analysis by 1.5. Some of them that we are more certain of will be multiplied by 1.2 rarely, like if you have a tank for liquid that is not dangerous, like water, the weight of the water will be 1.2, for instance. But the self-weight of the structure would be like 135. So if you would sum all of that together, on the load side, it would be like 145 maybe combined, because most of the load is the load that you can change, so that would be like 1.5, and some of it will reduce it. And then on the material capacity side, sometimes we use 1.1 safety factor that is additional, so it would be 1.1 times 1.45 maybe. So I would say that we are somewhere there when it comes to the safety factor level. Although in civil engineering, since we always do one-off designs, the biggest emphasis is this has to be safe. So while getting something below this safety factor will be frowned upon and, like, on a worst case scenario can get you in trouble, if you severely exceed the safety factor, most likely nothing will happen. So there, I understand that in planes that would be super bad, right? In civil engineering, it's not great as well, because somebody overpaid for the structure. But sometimes even the customers, especially on the industrial side, will tell you something like, I don't care how much the structure cost because it's cheap compared to what we do. So just, you know, make extra certain that it will work, because we don't want to strengthen it in 10 years or anything. And then that would be like a difference in approach, perhaps. That the upper limit of safety factor is kind of vague. Like, we don't have a guidelines which says, oh, if you exceed a safety factor of 2.5, you're in trouble. That wouldn't happen most likely.
No, understood. I mean, that's a distinction again, isn't it, in terms of the way that the structures are. Okay.
Maybe I should add that this usually works in industrial design as I practice. Although if you would manufacture typical grain silos, for instance, that you manufacture not for a specific customer for specific use, but there is a catalog and a farmer can buy like a silo from a catalog and you already have it done and you basically sell it to them as a product. Then those, of course, are way heavier optimized and then the safety factor of 2.5 wouldn't fly at all. But if you're doing like one, but it's not one-off design in such a
yeah. Cool. Okay. Yeah, good stuff. Okay, well, we've got a list of questions here that we've discussed beforehand. Is it 50 or 60?
Hopefully I know the answer.
50 or 60 questions, was it? I can't remember. 4-hour podcast. No, just a select few here. I mean, one that jumps out to me now that you've spoken about your background and how the company's developed and your sort of step into training and what have you. How did you get involved with FEA yourself in the first place? What did your learning profile look like?
That's a grim story. When I was a student, we of course had an FEA class, which basically looked like a lot of matrix operations. I would divide it into the mathematicals, the math itself. We had like matrix operations on another subject. And then somebody came and said, like, if you're doing FEA, it's this matrix operation, that matrix operation. You know, I don't think that we ever did it in front of a computer.
Wow.
Well, I had one laboratory class where you get like a 10-page instruction and it says, click here, click here, click here, click here. And that would be the whole thing.
Yeah.
So when you would catch me on 5th year of my university just before PhD and tell me like, what do I think about FEA? I would tell you that's nonsense. It's like theoretical stuff for people who have nothing better to do. I'm a practical guy. I do design. That's absolutely not what's useful.
Yeah.
And then I started my PhD and my thesis tutor.
Sorry, Lucas, just if I can ask a question on that then. So you were learning the basics of the numerical procedure.
And then such big basics that I wouldn't be able to make my own solver. It was more like selected topics. It was never coherent enough to write a solver. It was just like, you know, few points here, few points there.
That's what I was going to ask, because I remember some of the stuff that I did very early on. We did look at some very simple code development for beam type structures. So we looked a little bit at the maths, a little bit at the numerical processing, and then a little bit of the computational processes, if you like.
Sadly, we didn't do even that. We just had like few random classes.
Yeah.
And then when I started PhD, my wonderful thesis tutor told me, look, Łukasz, this is like 21st century and you're doing a PhD. So not only will do lab tests, you will also have to do FEA to correlate with the lab tests.
Yeah.
And my instant thought was, oh my God, mathematics. Like I hate complex mathematics. Like at some point in my life, many years ago, I was like kind of okay-ish with it, but I hated it.
Yeah.
So like I literally like I was on the verge of crying, but I'm a workaholic, so I was like, okay, sure, I'll do it. So we had a Abacus license at the university.
Yeah.
So I downloaded it and started to playing around. It took me like a year and a half to converge first analysis, literally, because shell buckling is insanely complicated, but nobody told me that.
Yeah.
And of course, like a stray 8 student, I simply assumed that I will do the model I supposed to do without anything in between. So I instantly started at a very difficult thing.
Yeah.
And I literally grinded it out. I had Excel sheets where I wrote like, if I change this parameter, this happens. If I change that parameter, I literally did it with trial and error. And it took months.
Yeah.
And I then converged my first analysis. I don't recall even what it was. Like it was like some lab sample, but maybe it was like nonlinear geometry, like arc length stuff, right? And then I went to Polish Academy of Science. My thesis tutor arranged me like a show and tell there. And it was like a group of, I don't know, 50, maybe 70 professors, like all the best specialists in the country, and me presenting my FEA. it was all wrong, but at that time I had no idea about it.
Mm.
So everybody was super happy. I got like standing ovation and stuff. And
Wow.
and only one professor afterward came to me and say, "Hey, mate, look, you're just about to defend your thesis. That's awesome. So defend it, and then after you do, this is my card. Call me after you're done." So I said, okay. I defended my thesis, reach out to the guy afterwards, and he said, like, "I didn't want to tell you that beforehand because I wanted you to defend with clear conscience, but you really should read like a few articles by Professor Rotter because what you're doing sucks, man. Like, this is not how the game is played."
Wow.
And I was like, "Oh no, seriously?" And he said like, yeah. So then I spent like 2 additional years learning how nonlinearities work, understanding this from like math and scientific articles. And at that time, I already had my company for a few years. So I started to realize that there are practical applications. First, like I already had a PhD, so first silo design projects happen. And I started to see why it's impossible to calculate them without FEA. I started to encounter the practical problems. And then I realized that FEA can actually solve that for me. And so for quite some time, there was a parallel between my university work and my design work. Although it was like at university, I banged my head on the keyboard trying to figure out how to make it work. And on the business side, I just had to do whatever to finish the designs. And that's how it started.
One thing, I mean, there's a parallel there with yourself and me as well, in the sense that when I started my postgraduate, my doctoral studies, I had an abacus license. I didn't have anybody around me who knew how to use it. You know, I've mentioned on a couple of other people's conversations, big stack of abacus manuals.
Still have them.
Have you? Mine are up there. Yeah.
It's like you can build a bulletproof vest out of them, but it's very heavy.
that would be funny. That would be funny. That would be a good LinkedIn post. How fast you could shoot through an abacus manual. Yeah. Let me think. So, I mean, did you do any formal training in terms of your abacus usage? Did the abacus reseller locally have any classes or anything like that you could do?
No, I never did that. Well, for one, I didn't have a commercial license.
Okay.
So I had like scientific license. So I was a B grade user, let's say.
Okay.
And my university wouldn't pay for my training anyway, regardless. And since I couldn't afford abacus license to use commercially, there was no point to train in it other than for scientific reasons. Luckily, I've became a little bit known that I do shell calculations with FEA.
Yeah.
And then a local reseller of FEMAP reached out to me and say, "Hey, do you want to write a book for us?"
Oh.
And they provide me with a testing license that I could use to write a book. So I basically taught myself how to use FEMAP and then wrote a book. And at that point, I was already like efficient enough in FEA that I realized that I want to have like a Nastran license to do the calculations for shells and stuff. And that is how the science and the business merged in my career. And a bit later, I quit science because there was nothing else to gain, basically.
Yeah, okay. Now, lots of things spring to mind from that. Yeah. I mean, one thing is, how did the experience with abacus help you with the FEMAP Nastran?
Oh, tremendously.
Yeah.
That was like, this is why I'm so certain to say people that the most important things about FEA are completely solver independent. It took me like 2, maybe 3 years to use abacus to any practical ends.
Yeah.
And it took me like 2 months to learn Nastran, simply because I already know what I needed to do. I understood the process. I knew what I was looking for. So the only thing that remained was, where the hell do they have the button that does X? And then when you know, like, finding the button, like, you can literally search on YouTube, like, where the hell is the button that does this in, like, whatever software, and most likely the provider of the software has like 2-minute video that shows you where the button is.
Yeah.
The video doesn't tell you what the button does, but if you know that and you're just searching where the button is, you're gold. So it went extremely quickly. Like, the first experience I have in Nastran was calculating the examples for the book I was reading about how to use Nastran.
Yeah, amazing.
So it was not a problem at all. It's only about understanding.
But it was the foundation in the model build, the solver architecture, what to look, how to verify, how to understand the output. That you learn
how the solver works, how to iterate solutions, and so on.
Yeah. No, that's interesting. Yeah. Okay. So the teaching that you do now, then, you're very much focused on non-linear analysis.
Mostly, yes. Well, I have an online course about basics of FEA as well.
Okay. Yeah.
But then I do non-linear FEA stuff as well, and that would be the thing that I like the most. Let's say that's the, like, if you would hire me to do like a live training, the one I enjoy the most would be the non-linear FEA, because it's just fun to me. It appeals to me. And that's what I do.
There are more things going on, more considerations, but when you understand those well and you can guide somebody through that maze, that's pretty satisfying, isn't it?
Oh, absolutely. Yeah. It's wonderful when, especially since very often people start to learn non-linear FEA because they're desperate. They've been doing linear FEA for a very long time in civil engineering. That's not sufficient. And finally, somebody called them out and say, look, that's like, you can't have that. You can't ignore this. You can't pretend that. You need to do it the right way. And they learn, oh, gosh, I was doing this wrong. Now I have to do it the right way. I don't know how. And they find me. I come and show those people, look, you had to ignore this problem for all those years. I can explain why this actually works and what to do so you don't have to ignore it anymore. So there's like a psychological aspect to it as well, that people kind of feel more confident in the design in general, not necessarily in FEA, but in general, the engineering makes more sense when you understand. So that's cool.
Yeah, absolutely. Yeah, okay. I mean, one thing I did want to ask you, and we touched on this before we hit record. So perhaps if I can explain from my side, looking at, again, I've talked about wing structures. So looking at a wing, when you're developing a wing, I think back to some of the commercial aircraft programs I've been involved with, you might have tens of thousands of load cases. Okay, the wing is doing all sorts of different things, aerodynamic, wind pressures, mechanism movement, all this kind of stuff. And therefore, the challenge is to handle that design space. Okay, so currently, and I'm not saying that this is going to remain the sort of status quo in terms of the future, certainly with a lot of the data science stuff that's coming in, but basically, you constrain your design such that the structure works. So we talk about envelope cases. So these are the edge cases that are the nastiest cases. We don't worry about the ones in the middle because they're not as severe as the edge cases. But when we're developing and thinking about designing structure, whether it's manual optimization or automated optimization techniques, we will look at ensuring that we never approach yield, so we never have a load redistribution in the structure. I mean, there's many issues of that from a fatigue perspective.
Low cycle fatigue.
Yeah. So we always stay within the yield limit. We don't design for instability. So there's lots of structure in an aircraft that could go unstable, but we design within those stable limits. Okay, and then the other typical class of non-linearity within FEA in general terms is contact. So we assume things pretty much stay together. We don't have any gross movements or things that are really going to change the load path. So from an aerospace design perspective, we can use linear FEA, so material in it, all those things to develop a structure. We only really go to non-linear when there's either a problem in manufacture, a problem in operation, where we need to go, oh crikey, something's failed, we've got load distribution, or something's buckled, we've got load redistribution. So I've always seen non-linear, like I say, as something you do if there's a problem, rather than something you use as an initial design tool, if you like. And I think you suggested from the conversation we had again before we hit record that that's perhaps not the case in the structures that you look at.
Yeah,
is that right?
It's absolutely different in civil engineering, and this developed on several different paths, I would say.
Yeah.
Firstly, when you design quote unquote beam structures like factories, steel buildings and stuff like that, you can instantly use plastic section modulus, which basically assumes that you will yield the section throughout in bending. And that's like a vanilla most use case that happens all the time in most buildings. Okay. Frankly, plastic redistribution of stresses is one of those factors why most of the designs haven't collapsed yet. And then you do have buckling and you need to prevent that. In beam structures, that would be relatively easy, although we are allowed to calculate post-buckling behavior. So you can have a beam with a very slender web. The web buckles, but the beam still is operating. And there are rules for that. Yeah. So even within beam structures, we very quickly go into the non-linear, although many engineers wouldn't really understand the concept. They just follow the code that allows them to do that. Okay. And that's problematic in its own way.
Yeah.
And then when you have a big structure, is actually susceptible to big movements. And then second order effects from geometry when the structure deforms heavily. Like you can have like a very slender, very tall building, for instance. And that's something you simply cannot neglect because it would be dangerous to the structure itself. So that would be, even there, we would reach non-linearities. But when you do things that, like I do, like pressure vessels, tank, silos, shells in general, but also plated structures, those are often stiffened. And then at the tips of those stiffeners, you instantly get stresses higher than yield no matter what you do because because of the stress concentrations. And many people simply say, oh, that's a stress peak and ignore it, but sadly that's obviously not the right approach. You should use like non-linear FEA to see how this works. And there are failure mechanisms that you can encounter like plastic collapse or shell buckling, and to realistically analyze those, especially since shells in civil engineering tend to be very slender, you actually absolutely need non-linear FEA. There is there are equations in the code, but there are so rudimentally and so governing safety factors that if you want to have an economical design, non-linear FEA is basically a must-have. And and we do it not when something fails, we do it at the design stage. So we want to optimize the structure. So maybe somebody will use like a first approximation and do some simple equations simply to guess the initial structure more or less. And then they will do the non-linear FEA to optimize the design. So that's like in my company, we basically never use linear FEA unless we're debugging a model or something like that. We simply instantly assume that everything that we do will require non-linear approach.
That's that's a big difference, isn't it?
Oh yeah, like the computing time, for instance.
Yeah. Okay. No, I mean, I'm trying to wrap my head around a beam structure being able to go plastic, through the full section.
It is like that. It's crazy.
How does that not then lead to collapse?
Oh, if you need to have like over stiffened structure, and then a plastic hinge forms, and the structure simply rotates around the cross section that was yielded to redistribute the load somewhere else.
Yeah. Okay.
And that's I must admit that when you use plastic redistribution this way, that would be the higher end of design.
Yeah.
But till the first cross section yields throughout, that would be like absolute basic. Like software that does civil engineering design to the code by default assumes that you allow this.
Hmm.
Yeah. There are instances when you can't, when you have slender cross sections and so on, but normal sections are allowed, and that would be like the basics.
Yeah. Okay. So the nonlinear models that you develop are allowing all of these things to be happening. It's effectively structure, geometry change, and load redistribution all the way through.
Yes, for the shell and plate structures, yes. For the beam elements, you basically need nonlinear geometry, but you don't really need nonlinear material because the stresses will be like checked and the plastic section properties will be used to calculate stresses in the cross section. So you basically can do material linear analysis, and then in post-processing, when you check cross sections, you kind of account for the plasticity. So unless you do like plastic hinges and plastic redistribution in beams, linear material is sufficient.
Okay. So if you're then looking, everything you're doing is nonlinear. So you've obviously got load incrementation and load iteration all the way through the solution. So I mean, it depends on the analysis, obviously, but a nonlinear model could take computationally 10, 20, 50, 100 times longer than a linear model.
Oh, easily. Yeah, absolutely.
Easily. Yeah. Okay. So does that then give you a very different way at looking how you actually build the raw FEA model in the first instance? Then, are you forced to try and use the coarsest mesh while still giving you results?
No. Like, well, not in my company, at least. That depends on how much time you have, but I wouldn't take the job that would force me to do that. So effectively, what you do is you mentioned that in aircrafts you have like thousands of load cases. We have in pressure vessels, tanks, silos, there is like one big governing load. That would be the bulk solid, the pressure, the hydrostatic pressure, what have you. And then there are like additional loads like wind, snow, live load. Of course, earthquake is like a separate consideration, but even that, all in all, if you're reasonable within 1-2% accuracy, you can downgrade the problem to several load cases, maybe 10. Depending on the structure, of course, depending if you have earthquake, because it can happen in various directions. So if your model is axially symmetric or not plays a role, and so on and so forth. But even if it's not, you can basically use engineering judgment to say this and that direction are the worst, this kind of deal. So you kind of you have to think through what you're doing, and the engineering judgment happens at the level of how many load cases you wish to analyze. And we can quite greatly reduce the amount of load cases. But when you have that, there are no compromises when it comes to mesh quality. So I could build a model that would run nonlinear analysis in like 20 minutes, maybe. But the mesh would be so bad that the outcomes from the analysis would be basically useless. So we build models that are very nicely meshed, and they run for like 3, maybe 5 hours each. So effectively, what you do is you have several computers with several licenses, and we have very strong machines, and you run several analyses in parallel, and you simply run them overnight. So you prepare everything, run them through the night, and next morning you come to the office, you see the outcomes, you write portion of the report, you fix whatever needs to be fixed, if that's the case, and run again, and so on.
Yeah, gotcha. Yeah, okay. So my thinking then around simplifying the model is not the way to look at it. Well, I wouldn't say you simplify the loading, but you envelope the loading.
Yes.
So you don't need to run as many load cases, but you can have a higher fidelity model so that numerically what you're looking at is robust, and you can make judgments then from that.
Yes, but then it's not the envelope of the load in case of such models usually is not such a huge issue as you would think, because when you have a bulk solid in a silo, that's like 90% of the stress in the whole model anyway. So how you combine wind and snow has very small impact on the outcomes. And of course, if I would follow the code rules, I would generate like 800 load cases, and 790 of them are not governing anything.
Yeah,
And
yeah.
it's just a matter of figuring out which 10 are the ones that you need to analyze. And that's it, basically.
And again, we talk about the complexity of FEA and the solution architecture and all this kind of stuff, but ultimately it is a tool, and the skill of the engineer
absolutely
to look through the problem and use that tool in an efficient, effective manner that works for you. If you were going to run those 100 load cases and you press go, and you've got some massive cloud solver capability, but you're still taking a week to find the results, it's not going to work for anybody, is it?
True, but also there was a wonderful study that I often cite when it comes to this. They took 150 best cancer professors on the planet, divided them into 350 people group, and they took like a test patient, and they did run all the tests for the patient. For the first group of professors, they only sent like half of the medical documentation, and they asked them to say if the guy has a cancer or not. So it was like 50-50 chance.
Yeah.
And the professors, of course, said, hey, mate, like this is stupid. Like it's only half of the documentation. Why didn't you do this test, that, and so on? And they say like, look, this is all you have. Just provide me with yes and no, and the percentage of the chance, what you think, how accurate you are. So the first group, having half of the documentation, said that they were right, as you would guess, 50% of time. But they also reported that they are more or less 50% certain about the answer. And then they've made 75% of the documentation to the second group. And they again were 50% accurate, but they said that they are 75% sure about the answer. And then, as you can imagine, they sent the full documentation to the other 50, and they were sure, they were correct, more or less 50% of time, but they were absolutely certain that they are correct. So to me, when you analyze 200 or 500 load cases, this gives you like the full documentation. You think in your head, oh my, I analyzed it so accurately. Everything's there. It must be right. But in reality, how many of the outcomes of the load cases will you even look at? It's too many. You don't have the time and resources. So instead of dialing in on the most important problems, you just drown yourself in the amount of data you have no way to analyze. And this creates a false sense that you analyzed it, while in fact you just did it. And that's where I think that the engineering judgment and reducing load cases is significant, because then when I run those 10, I can actually look at every one of those, think if it's okay, if I like it, what I would change, and I can actually analyze the structure and not only look at the envelope of God only knows how many outcomes.
Yeah, that's a good point. That's a good point. Yeah. I'm just thinking we need aircraft to fly in a more stable way. So we only need 20 cases to analyze. That's not
I can easily assume, I can easily understand that in your industry, this may not be achievable, but in mine, it actually is.
Yeah, of course. Yeah. No, fascinating, Łukasz. Thank you. Yeah. Good stuff. Okay. We have one last question that we haven't touched on.
Okay.
To do with learning FEA. So we've talked about, some of the pain we've gone through. I mentioned to you before we hit record about conversations I've had with people that, they're looking at 2 weeks to deliver a software training course, and everybody is falling asleep in the class and blah, blah, blah. So these days, that young engineers or engineers moving from different disciplines, that there is a huge amount of learning, training, information available for people to get into their brains, so they're not spending 2 years learning how to converge an abacus model, But do you think there are still obstacles to learning for people coming into FEA these days, or what are those obstacles, would you say?
There certainly are. Like, thankfully, FEA has extremely steep learning curve. And it's thankfully because I'm already past it. So it reduces the amount of competition you get, obviously, right? And let's be honest, if the skill is simple to get, it's not very valuable. So the value of FEA actually comes from the fact that it's difficult to learn, because If it would be simple, everybody would be doing this, so the prices will go to the ground, obviously. And so luckily, there are problems. And I think that the first one people will encounter is what to actually learn. And the problem there is that if you studied engineering, like you or me, we actually encounter a course that taught you some glorified way of mathematical operations in matrices and all the differential equations and God only knows what else, right? And young people start to think, hey, since university taught me a little bit and only that, this must be the most important fact. And they buy like Crisfield volume 2, and they start to dig into all those equations I couldn't read to you because I don't know the name of the operators, right? and they start to, take the pencil pen and they start to derive those equations and learn that, right? Because that's what university kind of suggested. And you can spend decades doing that. And even assuming that you finally learn all there is, that gives you basically nothing. The solver is already written. If you want to have a design, you don't, if you want to write your own solver, there are good careers in this field. Learn it, become the best, optimize the Nastran or Abacus nonlinear algorithm in a way that it computes 30% faster, you will be rich. No worries, right? But that's not an engineering career, it's an IT job.
Yeah,
but
yeah.
There is a field, sure, but it's not for engineers, I feel.
Yeah.
And then on the other hand, when you go to software vendors, they will tell you something like, well, not all of them, obviously, some are honest, but very often you will hear something like, our software does it the best. You don't have to worry about anything. We have this magic wizard tool, and you press next, 7, 8, 11, play, and that's how you design stuff, right?
Yeah.
And you start to think, okay, this software has like 10,000 buttons. If I learn all 10,000, I will be an expert, right? So you start spending time on learning where the freaking buttons are. And while this will make you extremely efficient, God knows I know way too few buttons in my FEA software, but you will efficiently do stupid things, but efficiently nonetheless, right? And the truth is that that's being an engineer is what is important, to understand what you're doing, how you want to support your model, how you want to load it, what outcomes mean, and if they make sense. And there are no buttons in the software that you can click that print out, yes, it makes sense, no, it's stupid. Just as there are no equations you can derive that will give you a 0 for a stupid answer and 1 for a correct answer. So there's something else. This is like a triangle. And I'm not saying that theoretical knowledge is stupid. I'm not saying that software usage is stupid. I'm just saying that the most important thing is like the engineering approach to it, like the thing that doesn't depend on the software, like understanding what you're doing. And then so the first biggest difficulty would be to understand this part. And when you understand that, you're already way above and beyond the curve. So then it's where to learn that. Because you can't buy an FEA book that will teach you how to properly support your model. It just doesn't work. There are no such books, right? And you can't derive an equation that will tell you how to support your model. This is not how it works. You kind of need to know it. And you mostly know it by following like workout examples. Like you can follow, like join courses like mine, or you can read blogs and search for where somebody solves something explaining why they did it. The problem is that YouTube, for instance, is full of tutorials which says, oh, I'm clicking here, this parameter is 7, this is 9, this is 11, and let's move on, right? And if somebody doesn't tell you why it's 7, and then you will never know if it should be 7 in your case. And like copying this in other cases is plain dangerous. I actually had people that I reach out to and say, look, you should really delete that video because it's dangerous for people. This is not how it works, mate. So the certainty of outcomes of the data you get, like it's very easy to look like an expert on the internet, right? It takes conviction in voice and not caring about stuff and like a good camera. And you're an expert in whatever, right? And then like finding people who actually know their stuff and they're doing it and they understand it. It's important. And then learning those things while the most difficult, because this is the knowledge that is most difficult to acquire. I feel that would be the thing. So yeah.
It's again, it's a mix of theoretical knowledge, practical application, software usage, but most importantly, the ability to be able to look at your model, look at your output. Does this one reflect what I'm trying to achieve? And two, has it done it properly? You know?
Yeah, absolutely. And then there is this beautiful drama that people in mathematics know, that if you can calculate a very difficult differential equation, this instantly assume that you know how to add, multiply, square root, and things like that. You have to, because otherwise it won't work. In FEA, it's not the case. You can learn how to do insanely complicated analysis and still run it on a stupidly supported problem.
Yeah.
And one would think, oh, this is such an expert level FEA, like, you know, explicit crashes and so on. But then at the background of it, the thing that you do makes no sense whatsoever. So the basic skills, that's why I actually have two courses. Like the basic one is not necessarily simpler than the complicated one, because it teaches you different things actually. And people often assume that expertise comes from the fact that you know how to do explicit crashes, for instance. While realistically, I have a friend who acquired the Dyna, and he just pressed play. In 20 minutes, he calculated the crash of entire ship into a pole. And he said, like, it's like cheating. It's like computer game. You just press, and the only thing you can't be certain is what the outcome is. But apart from it, it looks great, right? So that's the issue there, that if you think that, oh, this is a complicated analysis, so it has to be right. Well, sadly, no. And that would be also a big difficulty.
I mean, I'm just thinking now, there's almost like a, 20, 30 years ago, simulation capability and what people were doing was at one level, and now all these different multi-physics problems are coming in, and it's made me wonder whether there's naturally a lag behind the skill set of people that are using it and the way the software is developing.
I think lag would be an optimistic assumption. I think it works. Yeah, seriously, man. Because lag would indicate that in few years we'll catch up.
Okay.
And to me, I feel that if you had like one of the first automobiles, when you bought it, most likely the dealership will instantly explain to you how everything works and how to fix everything. So on the road, you had like a screwdriver, like, few tools, and if something broke, you were the guy able to fix the damn machine.
Yeah.
Now if you have a modern car, if you go to car dealership, they have no idea how to fix your car. They need to hook it up to the computer, check what's even wrong. They need the car to tell them what's wrong. And then they won't attempt to fix it. They will just replace the part with a new one, right? So cars are better, but our understanding of cars, not necessarily, especially my understanding of a car as a driver. Right? And I feel that, like, I'm a big Warhammer fan, as most engineers, I guess. So 40K, the reference that you can have like starships that are repairing themselves, and after millennia, humanity forget how they work. So they actually sacrifice humans to offer them to the spirit of the machine, so the starship will take them to another planet, right? And I feel that if we develop those tools too fast, they will simply become magic. And people then will sit in front of the computer, perform some sort of engineering rite or a ritual, press play, and get the outcomes. They will worship the outcomes, print the report, send it out. And there will be less and less engineering involved because the complexity of it is too high. It's like, I'm an engineer. If I would be to fix my laptop, I'm not an engineer. I'm just a guy who can buy replace parts. That's not the same thing. Laptop is too complicated.
I mean, we haven't even mentioned AI. But what you just said there about the simulation becoming so evolved and so remote from people's understanding that we just have to believe it. There's a danger.
I'm a religious person, but I don't like believing in outcomes. I have to understand the outcomes. That's a completely different thing. And I don't feel that AI will solve our problems. If anything, it will make things worse, because it will give you the false, like, this is where they introduced automatic code checking in software. When I was starting, it was almost never done. You just did static and then Excel sheets calculations, right?
Yeah.
And then now you can press play and the software will display code checks. And then you can open the code on the training and tell the people, look, code chapter, this equation, that, you have to choose this or that, right? What would you choose? And they say like, oh, we don't know, it's difficult. And say, yeah, that's true. But your software didn't ask you for it, did it? So it made a choice. What did it choose? And why do you don't know about it, right? And you can pinpoint like dozens upon dozens of those places. But they say, yeah, but it's automated. I'm like, if you have automatic gearbox, it's automated, but it doesn't prevent car crashes. Like, it's just automated. Like, it's not, automated doesn't mean correct. It means automated. And people very often think if it's automated, it must be right. And that's very dangerous. So yeah, that's nothing like a pessimistic outlook at the end of the conversation.
We've covered religion, spaceships, the future,
human sacrifice.
What else is there to simulation and analysis?
I used to joke that sometimes you should have like a sacred set of chicken bones, and when you can't converge your analysis, you throw the bones to see what you're supposed to set after.
Amazing, Łukasz. Amazing. Good stuff. We've covered a lot there. I've really enjoyed that. Really enjoyed it. Thank you for your energy and your fantastic view on simulation and what it means to people, you know. So
thanks for the invitation, man. It was such a pleasure to be a guest here, and to all of us, all of you who are watching us, thank you for sticking up to the end. I hope that you enjoyed it. And yeah,
excellent.
Thanks, man. I really appreciate it.
Cheers.
Take care. Have a wonderful good day.